Hello, everyone. My name is Dr. Nagman Khan from the marketing team here at SimScale. I hope you can all hear me and see the slides all fine. Uh, I'm delighted to be joined by my colleague, Kyrie, who is an application engineer here at SimScale. Kyrie, hi. Thanks so much to Kyrie for joining us and to all the attendees. Let's get started on the webinar. First of all, I'd like to introduce SimScale quickly for those of you who don't know us. SimScale is a fully cloud native engineering simulation platform. Okay, and we make simulation easy for architects, engineers, and designers all over the world. And today's application is looking at thermal and building fabric performance. Before we jump into that specific topic for today, I did want to quickly direct your attention to a couple of resources we have that you might find interesting. If you signed up for this webinar, these related topics will definitely be of interest. You can go on the SimScale website. We have a couple of white papers there, for example, simulating the indoor environment. And there you can see in more detail topics such as room thermal comfort, air temperatures, how to use CFD, computational fluid dynamics, to simulate the indoor environment in buildings, spaces, rooms. Also things like occupant comfort and common metrics like PMV, PPD. Building envelope heat transfer is something we'll be looking at today. And today's webinar is really off the back of a new feature on wall heat flux that we released recently, which my colleague Kyrie will be talking about. And this was the first webinar where we're really telling everyone about this feature. In the near future, around November time, we'll do a more detailed analysis using this feature where we'll also be showing some thermal bridging calculations. Okay. Other topics that you might find interesting are things like indoor air quality, for example, simulating the spread of CO2, natural ventilation, ventilation efficacy. We have architects and engineers using SimScale to model things like window opening strategies, for example, okay, data center cooling, simulating fans and mixed mode performance. So there's a lot there that's useful for anyone joining this event today. Today's topic specifically is about the thermal performance of the building fabric and how SimScale can be used to model the impact of heat transfer on your building designs using cloud native simulation accessed through a web browser. Okay, so we're going to show you how CFD can be used to model various heat loss predictions, wall heat fluxes, and let's take a look at how to model the thermal performance of a building fabric. So if you just give me a minute or two, I'm going to hand over to my colleague Kyrie, who will be doing a live demonstration of the SimScale platform. One other thing, you have a questions panel there in the GoToWebinar screen. Please feel free to start posting questions as and when you think of them, and we'll cover as many questions as we can at the end of the session. Thank you.
Okay, perfect. Thank you very much. Thank you for this informative introduction and a warm welcome from myself to everyone who's attending the webinar. Now let's jump into the really interesting part of this webinar where we are going to talk about how we can utilize SimScale to really assess the performance of a building fabric. So in this case, we are going to analyze a multi-story building where the main objective is to really quantify the total heat loss from surfaces and rooms in the building so that we can understand what is the efficiency in regards to this building fabric. Now, also since SimScale is a cloud-native solution, it's important for us to also demonstrate how parallel simulations in the cloud can really result in basically demonstrating a huge benefit, especially in time saving and efficiency at work. Excuse me. Now, the case that we are analyzing here, as I said, it's of a multi-story building. We are focusing here on the room on the top corner, where we are analyzing a winter scenario. This winter scenario, basically, we have an outside temperature of 0 Celsius degrees. We have a supply inlet at 10 liters per second at 22 Celsius degrees. Moreover, in this building, we have some heated floors in the first and the second. They are also at 22 Celsius degrees. And essentially, the design parameters that we have in the simulations are the roof, the windows, and the external walls, where basically we are analyzing different think of them as building materials, right? So for example, for the windows, we have either a single or a double or triple glazed windows. We know their U values, And then we feed this information to the simulation so that we can understand how that essentially reduces the total heat loss from this building in this case. Because now we are analyzing a winter scenario, we know that we have this outside temperature, the temperature inside is going to be higher. So we're going to be losing heat to the outside, and we want to minimize this heat loss. And how are we going to do that? We are going to do that using this really newly released feature in SimScale, which was quite highly demanded from our customer base because we know that there is a high benefit that comes from it, which is essentially the wall heat flux output using the robust conjugate heat transfer solver. So that's basically the description of this case that we are going to analyze. And now if I move on, we see over here a more detailed explanation on the actual cases that we are analyzing. So as I mentioned, we have three different variables that we are studying, which are the window glazing, exterior wall, and roof. Now for the base design, we're going to be focusing basically now in this demo on two design variations, which is the base design. It consists of a single glazed window and no insulation on the external walls and roof. And we are going to compare this base design with variation number 6. Variation number 6 has a triple glazed window and external walls that are insulated using phenolic foam insulation, and we have also an insulated roof. Now, all of these simulations that you see over here were run in parallel, and I will demonstrate that later in one of the slides. But for now, I'll take this chance to jump into the live demo, which is the part that I'm excited about the most. So let's go ahead and jump into the SimScale dashboard. Now you see over here that I essentially just changed tabs. And this is because, as I mentioned, SimScale is a cloud native solution. And what does that mean is that all you need to access it is essentially an internet connection and a browser. And why is this important to you as a user? Because we all know that CFD simulations are in general heavy. They requires proper computing machines to run these heavy computations on. And this by itself requires an investment. Now, this investment with SimScale is completely eliminated because everything that we do is running on the cloud, on actual servers, and all you need to do is just have a very moderate computer and an internet connection. Now, to access SimScale, you can log in with your email and password. And over here, we are looking at the dashboard. So this is essentially the place where you get access to the projects that you are working on or the projects that have been shared with you by your colleagues. Now I can go ahead and search for the project that is interesting to me, which is the building fabric design. And once I access it, I jump in now to the SimScale workbench. Now, I'll give a brief introduction to what we are seeing over here. So on the left-hand side, you get access to the geometries that you upload. Also, under simulations, you get access to the simulations that you had run. So for example, under each simulation, you have the settings of this particular simulation that allows you to really make the simulation be as much corresponding to the real life scenario that you are trying to solve to make sure that you get an accurate outcome. Excuse me. And currently we are inside the post processor. So what we have over here is the wall heat flux, which is the output that I was discussing earlier. And we are visualizing we want to focus essentially on the wall heat flux on this particular room of interest. And what I am after now is to really see what is the amount of heat that I'm losing in this particular room. Am I losing a lot of heat to the outside? Because I wouldn't want that, right? We're trying to save energy, trying to make this building design efficient. And I can actually try to quantify this a bit by plotting a inspect point, and I see that I'm losing around minus 15. There is a heat flux of around minus 15 watts per meter squared. And just to make this very clear, the color map that we have, red indicates that we are losing a lot of heat. Blue indicates that we are gaining heat. And we can see here from the window that we are actually indeed losing a lot of heat. But by how much? Maybe I can check that directly by enabling statistics. And I see that I'm losing about 27 watts of energy through this particular window. And we also have this other window in the back, and we have the external wall. So overall, I could be losing a lot of energy in this particular room. So as a designer, I come up with a question. And for me, this is really the most interesting thing about simulations is because you can really answer all of those if questions that you have as a designer. Like, what would happen if I try a different design, if I try different materials? And I can go ahead and compare one of those materials. For example, I'll compare it with variation 6, and we will take a look at how much improvement do we have with variation 6. And just to remind you that variation 6 involved a triple glazed window, and the external walls are insulated using phenolic foam, and the roof is also insulated. And by taking a look at this, we clearly see a reduction, an actual improvement in the overall energy efficiency of this particular building and room in particular, where the amount of heat loss is greatly decreased by modifying the building materials. And we can visualize this. Now, for this particular case, we are seeing it for a simple sort of a facade design. But please remember that with simulations, you can analyze much complex facade configurations of your building. So you're not limited to any particular simple design. You can simulate whatever comes to your mind in order to make sure that you optimize your design and provide value to your clients. Now, that's mainly it regarding what did I want to show about the results. So let's jump back and see how we can set up one of those simulations. Now, the first step to set up a simulation is, of course, to upload the geometry. SimScale works robustly with almost all native CAD formats. So for example, whether you're working with SolidWorks, Rhino, CATIA, Creo, etc. Once you import your CAD geometry, you could go ahead and create a simulation. In this particular case, we are interested in the conjugate heat transfer simulation because we want to understand the heat transfer by three means: convection, conduction, and radiation. However, SimScale is a multi-physics platform, so you're not only limited to one particular simulation type. Everything happens directly on the same web page on your browser. No need to switch between different applications. So for example, if I'm interested in running pedestrian wind comfort analysis on building masses from trying to design the city, I could go ahead and choose that. Or if I'm interested in some static or structural analysis, then I could also go in that direction too. Now, let's go ahead and create a conjugate heat transfer analysis. When we do that, we get prompted with what is called the simulation tree. And the idea here behind it is that we try to make the simulation workflow for any particular user, regardless of their experience level, quite easy and intuitive. And this can be demonstrated by just thinking of this simulation tree as a system that you work your way from top to bottom. And everything that you need to do is to convert every red circle into a green check mark, and then you will be able to run your simulation. Now, we can go ahead and set up some of those boundary conditions. So for example, I know that this particular building is essentially filled by air. So over here, we have just the fluid domain inside that building. We are not modeling the solids in this particular simulation. Then I can go about and set some of the boundary conditions. So for example, I know that for my room of interest, which is over here, I have an inlet with a flow rate supply with what is equivalent to 10 liters per second. And I can set that up and define the inlet temperature as 22 Celsius degrees. Now, of course, I can go ahead and show all of these boundary conditions, but I would rather show you one of the already set up simulations that I had. But before jumping there, I just really want to emphasize the importance of this particular step under result control. So when you expand result control and field calculations, you get access to request extra information to be outputted in your simulation. And these are very important for every designer and building architect who's trying to optimize their building efficiency, whether it's using the wall heat flux to quantify the heat loss or heat gain, whether is it the thermal comfort parameters to understand the thermal comfort inside the house, or even to quantify the mean age of air. So sort of especially it has been relevant in the past years with the COVID and etc. So we want to make sure that everything is ventilated properly. So for this particular case, we are interested in the wall heat flux, and we set that up, and then we fire our simulation. Now let's go ahead and just check real quickly one of the already set up simulations, and I'll just go ahead over one of the boundary conditions, which is, for example, the windows. And the reason why I want to do that is I just want to explain how you can input those different U values and different materials into the simulation. So we are setting up a wall boundary condition using a derived heat flux where we are specifying what is the ambient temperature outside. But what is important for us is the conductivity thickness pairs, which is this layer wall thermal, where I know from basically from the supplier, I know what is the U value for this double or triple glazed windows. Once I know the U value, I also know the thickness. I can calculate the thermal conductivity and input this into the simulation. And this will act as a thermal resistant layer that essentially will incorporate the effects of this building material into your simulation. And as we saw, it adjusts accordingly the heat loss of the system. Now, I can go ahead, once I know this simulation is sort of finished, I can go ahead and run a simulation real quick. Once I do, you see that I've been running this for multiple design variations. So it's going to be a little bit cumbersome to go about setting up these boundary conditions for every one of them. However, you can benefit from the template configuration that we have designed here at SimScale, where if you know that you are happy with one of your simulation setup, you can essentially duplicate that and say design variation sort of 6, and you can just go about change only the parameters that you would be interested in changing. So I could drop this thermal conductivity by a margin, and then run now my new simulations. Essentially, you can run as many simulations as you want in parallel. And please remember that at any particular stage during your simulation setup, if you get stuck or if you need any assistance in setting up these simulations, please remember that you are not alone. You can always, and I do really encourage you to utilize our chat functionality, where you can send us any message and talk to us, and we will make sure that you get the most value out of your simulations. That's mainly it of what I wanted to show inside the platform. I would like now to jump into the slides to conclude with a few remarks, and then we go in straight to the Q&A session. Now, over here on this slide, again, we just see really a quick summary of the slides that I've just shown, which was the comparison between the base design and variation 6. We've already highlighted that in the windows, we saw the highest energy loss. We saw the highest energy loss in between the base design and the variation 6. And we saw how, for example, when we utilize double glazing or triple glazing, we saw a clear reduction in the amount of energy lost through that particular surface. What is interesting to point out as well is that we are losing more heat from the windows than from the external walls. So it could be an investment sort of to more focus on the actual windows than the external walls. Of course, that's up to the designer. And just as a reminder, we saw that this window had lost around 26 watts of energy. So to quantify this, that's equivalent to around 3 8 watts light bulbs working or basically being lit up inside your house. And finally, here on this slide, we see some sort of key outputs and comparison. So here we have some basic information about the base design. So the total heat loss in the base design from the windows, external walls, and the roof was about 103 watts. And for the variation 6, it resulted in a total reduction of around 33% in comparison to the base design. And over here on this table, we see a detailed analysis of all of the variations that we ran, which had been all ran in parallel and all essentially finished at the same time. So that's a huge time saving for the user. Instead of running each one serially, I can just fire all of those at the same time in parallel and benefit from the cloud computing functionality at SimScale. That's mainly it from my side. I'll hand over to my colleague Nagman so that we can commence with the Q&A session.
Kyrie, thanks so much for that demonstration. So please post your questions now. We already have a couple. Let's get through them quickly. Quick summary from what I can see here, Kyrie, is that the wall heat flux features, which are new now in the CFD platform, it's another capability, which we mentioned earlier. Do you remember when I was directing people to the white paper? There's lots of different indoor microclimate, indoor comfort, air quality, thermal, fabric capabilities now for architects and engineers, designers in SimScale, okay, which is a great thing. And we're continuously adding more as well. So Kyrie, we have a couple of questions. The first one is, you mentioned some CAD formats earlier, right? A common CAD format that architects and engineers in the building industry might use are, for example, Rhino, Revit, DWG, things like this. So these CAD formats can also be imported into SimScale easily?
Yes, especially for Rhino and Revit, we do have native support for these formats. For DWG, we just need to make sure that and understand that SimScale allows uploading CAD models that are three-dimensional. So as long as your CAD is three-dimensional, you can import these CAD models into SimScale directly. And it's also important to note that we do support generic CAD formats like IGES, STEP, and ACIS as well.
Brilliant. Another question is, can you just elaborate what you meant a few minutes ago when you said you could run all 6 of those models simultaneously? To someone who's not used to that, what can you just elaborate? What does that actually mean and what the benefit is?
Absolutely. So as you might have seen when I was demoing this live, you saw that I ran first the simulation of the base design and then I duplicated it and ran another simulation at the same time. So this is sort of what I mean. And you can repeat this process and run all of those 6 variations that you had exactly at the same time. Now, what does this really mean? This simulation that I ran took around 100 minutes. Now, in the old times, I would have to wait 100 minutes until the first one finishes because my computing resources are already occupied. Then once that one is finished, I run the other one. So that's a total of 600 minutes that I'm basically waiting until I get my results. But with the power of cloud computing and exactly what you can do in SimScale, because we designed a tool that is extremely robust in handling such analysis, you can run all of these simulations at the same time and you get your results after 100 minutes for either 6 or 60 or 100 simulations, regardless of how many simulations you run at the same time. I hope this clarifies this question.
Yeah, I mean that's amazing. The fact that you could run 20 different building models and they would all be simulated in parallel. So it would only take the same as running one model. This is extremely powerful. We have another question. Maybe I can answer this quickly about solar gain. So can you input and model solar gain? So yes, we can. We also have a solar calculator. This is a question from Swan Hodin. We didn't show it here in detail, but we have a couple of webinars in the past that you can search for on our website where we've shown how to model solar gains. Okay, and you can connect that, model that explicitly, or connect it to a weather database as well. So in a future webinar, maybe we have coming up in November, which is called Simulating Building Performance. That's on our website. You can register for that webinar now. In that webinar, what's interesting, Kyrie, is we're going to show pretty much all the features that people in architecture, engineering, construction industries can use in SimScale. So we're going to start from the outside, from the microclimate. So we're going to look at building aerodynamics, wind, pedestrian wind comfort, solar. We're going to come to the fabric, Kyrie, like you've shown today. So fabric performance, thermal bridging. And then we're going to go inside the building. So things like air quality, CO2, thermal comfort, air temperatures. So that will be a fantastic event as well. So do register for that. Kyrie, is there something you want to mention quickly on modeling solar?
I could just show the feature in action real quick. It's also very important to mention that we've hosted a webinar on this where we talk about it really in detail. But just to show you how it looks like, so for example, when you click on any of the conjugate heat transfer simulations that you've enabled, you get access to a toggle here called solar load. Now, once you enable that, you get access to the solar calculator where essentially you define your location. So let's say I'm in Munich at the moment, and I can define the time and place. So now we are in October, etc., 2022. And you can define the direct and the diffuse solar load. So with this feature, you get access to define these two solar load variations so that you can incorporate these effects quite accurately in the calculation of the thermal comfort, or basically in optimizing your building fabric overall. Please watch the previous webinar that we have done on the solar calculator as we really expand really in depth regarding this feature and how it can benefit architects and designers like you.
Thanks so much, Kyrie, and I hope you.
Thank you.
Yeah, I hope that answered your question. So we've run out of time. Thank you so much for attending. To all the attendees, you can, if you haven't tried SimScale, we have a free trial available on our website. Feel free to go on to simscale.com or get in touch with us. You can contact us at sales@simscale.com if you'd like a free trial or a more detailed demo for yourself, your team. If there's any projects where you're working on where you think that SimScale might be able to help, we'd be happy to assist. Thanks so much for joining, and we wish you a good day.
Thank you very much. Take care.